Welcome to Dynamics Part 6, Free Body Diagrams. Body diagrams are nothing more than sketches or drawings showing all the forces acting on a body. And as you can see here on the screen, I have a box sitting on an incline and the forces that are acting on it. There's a force pulling this way, trying to pull the box down the incline. Force of friction acting in the opposite direction, going this way. The force that the box pushes on the incline with and the force that the incline pushes up in the box with equal and opposite. This is called the normal force in this case. The weight of the box acting from the center of mass of the box towards the center of the earth. And right here, if we complete this force triangle, is the applied force, the same force as here. Same magnitude and pointing in the same direction. Now as you can see, these things can be a little messy, so I drew up a little neater one right here. All the same components. Here's the incline, here's the box. The force the box pushes down on the incline with, the force the incline pushes up on a box with. Again, this is called the normal force, and this is in magnitude minus the normal force. The force getting the box to roll down the hill right here, the applied force, sometimes called the parallel force because it is parallel to the surface of the incline. Here's the force of friction, the opposite direction, pointing in the opposite direction of motion. Here we have the weight of the object acting from the center of gravity to the center of the earth. And the applied force again, it's equal in magnitude and parallel to this applied force right here. The angle of the incline is given right here as theta. And this angle in this force triangle is also theta because the incline and the force triangle are similar triangles and their corresponding angles. All right, by looking at this diagram, we can see that the applied force is nothing more than the weight of the object times the sine of the angle theta, and the normal force is the weight of the object times the cosine of the angle theta. Remember that weight is equal to mass times acceleration, so the applied force is mg sine theta, and the normal force is mg cosine theta. Example number 1. A 10 kilogram box slides down an incline with an angle of 30 degrees. The force of friction is 20 newtons. Find the box's acceleration. Right, starting at the very basics, we know that the net force acting on the box is the applied force minus the force of friction. And we know that the applied force is larger because if it wasn't, the force of friction would be holding the box back. The net force is equal to the weight of the body times the sine of the angle minus the force of friction, which we were told are 20 newtons. Net force, mg sine theta minus 20 newtons. Net force, mass of the box, we were told are 10 kilograms. G, 9.8 meters per second squared, times the sine of 30 degrees minus 20 newtons. Net force equals 98 newtons times 1/2, which is the sine of 30 degrees minus 20 newtons. Net force, 49 newtons minus 20 newtons, give us a net force acting on the body, 29.0 newtons. Now, to find the acceleration, we use Newton's second law. Net force acting on a body is equal to the mass of the body times its acceleration. We just calculated the net force, 29 newtons. The mass of the body is 10.0 kilograms. We're given that information in the problem. And we're looking for the acceleration. Acceleration is 29 newtons divided by 10 kilograms. Give us an acceleration of 2.9 meters per second squared. Example number 2. A 15 kilogram box sits on an incline. The force of friction with the incline of the box is 25 newtons. Question is, at what angle, theta, does the box start to slide? The free body diagram is given right here. As you can see, all the usual forces are here. We have the applied force, the force of friction, the force that the box presses down on the incline with, the normal force the incline pushes back with, the weight of the body, the applied force here, again equal and parallel to this applied force. Now, we know that in order for the box to slide, the applied force has to be greater than the force of friction. If it's not, force of friction is going to stop the box from sliding. The applied force is just the weight of the object times the sine of the angle theta. Has to be greater than the force of friction. Weight is just mg. Sine theta is greater than the force of friction. We know the mass is 15 kilograms. That's given. G is just 9.8 meters per second square, acceleration due to gravity. Sine theta greater than the force of friction, which is given to be 25 newtons. Multiplying these numbers out, we get 147.0 newtons. Sine theta is greater than 25 newtons. Sine of theta is greater than 25 newtons divided by 147 newtons. Sine theta is greater than 0.17. Solving this for theta, we get theta is greater than the inverse sine of 0.17. And using our calculator or working backwards through a table, find out that theta has to be greater than 9.8 degrees. Now sometimes you'll hear this function right here referred to as the arc sine rather than just the sine, or inverse sine. Okay, I hope this helped. Please feel free to leave a comment. Let me know what you think of it. Is it clear, not clear? More examples, the examples aren't relevant, and so forth. Thanks for your time.